Hello my friends, Terry Brainy Nerd Tutu here, and in our journey of the many ways to calculate entropy using thermodynamics, we need to know what the entropy of a substance is at absolute zero. And we say in the limit of absolute zero because we can never achieve absolute zero, but if we could, this is what the entropy would be. That's what we're talking about. Now, we need to know the entropy in the limit of absolute zero because this allows us to calculate the absolute entropy or the molar entropy of a substance at any temperature. Now, it's usually pretty simple. Many substances follow what's called third law entropy, and that is the entropy of a substance at 0 Kelvin, and the limit of 0 Kelvin is 0 joules per Kelvin. And this may seem unremarkable, but it gives us a base value, a number to start at when calculating molar entropies. Many substances have what's called residual entropy, and a residual entropy arises from a material that can have different states, different arrangements at 0 Kelvin, and there's no energy advantage to adopting the different states. So I have carbon monoxide as an example here. If we line the molecules all up in a row, the carbon can either point to the right or the carbon can point to the left. So there's two different arrangements for each molecule. And if there is only one molecule, there would be two possible arrangements in this scenario here, to the right or to the left. If there were two molecules, then each one can point to the right or the left, so there would be 4 different arrangements. Here's an example of different ways to arrange 3 molecules. So 2 to the power of 3 means there's 8 different arrangements or microstates. 1, 2, 3, 4, 5, 6, 7, 8. And in this series, we're sticking to the thermodynamic calculations of entropy, not the statistical analysis of it, but just to give you a little bit of insight, the statistical equation of entropy is entropy equals the Boltzmann constant times ln of the number of microstates, or the number of different arrangements. And imagine we had a mole of CO molecules, so we had Avogadro's number of them. Then there would be 2 to the power of a mole, or 2 to the power of Avogadro's number, different microstates or different arrangements. Now, if we were to solve this, we can move the exponent in front of the log using a log law, my favorite log law. And this is kind of cool. If you plug in Avogadro's number times the Boltzmann constant, we get the gas constant. And the gas constant is 8.3145 joules per mole Kelvin times ln of 2. And if we plug this into the calculator, we get 5.76 joules per mole Kelvin. So this is a pretty quick back-of-the-napkin calculation. We calculated the residual entropy for CO, 5.76 joules per mole Kelvin. Here. What does the experimental number give us? Well, experimentally, we get a number of 4.3. Water has a residual entropy of 3.4. HCl of 0.6, so 4.3 to 5.76. It's pretty close, pretty close. Now, how do we get these experimental numbers if we can never reach absolute zero? Well, these numbers here, these are calculated as the difference between the spectroscopic and the calorimetric methods of calculating entropy. We're going to use these third law and residual entropies in this series when solving entropy problems. Hope that helped, and I'll see you in the next video. Cheers.